All right, so this is very much like the setup we had for our lab yesterday. Okay, so what we're looking at is we've got no friction. Okay, so it says there's no friction. The hanging mass is 2 kilograms. That means that the force of gravity acting on the hanging mass is 19.62 newtons, right? 2 times 9.81. Everyone okay with that? Okay. They also tell us that the acceleration of the cart, and thus the whole system, is 2.15 meters per second squared. So, what does that allow me to calculate? Yeah, I can get the mass, because I know what the net force is. The net force is 19.62 newtons. There's no friction. The 19.62 newtons is the only force pulling the system. Okay, so I have F net, and I have the acceleration of the system. But when I find the mass, I'm finding the mass of the system. Okay, which is why when you do this, you actually get 9.13 kilograms. That's the mass of the system. There's 2 kilograms hanging over the pulley. Okay, so when we go mass equals F net over A, we go 19.62 divided by 2.15, and we get 9.13. And we have to subtract from that the 2 hanging kilograms, okay, off of that to get the mass of the cart, 7.13 kilograms. Right? So there's all kinds of little tricks that can go into these questions. But in the end, do we always do essentially the same things? Sum of all forces and F equals m times A. In every Newton's second law question we've done those 2 things. Okay? All right, I want to have you guys go back to a little bit of inclined plane stuff because we didn't really get to try many of those the other day. So today we're going to primarily focus on those. Okay, so I want you guys to have a look at two, 3, and 4 for right now, and then we'll walk through those ones together. Okay, so trying 2, 3, and 4. This is in your digital workbook, by the way. It's on page 3. Okay, so we're working on 2, 3, and 4 for right now. Okay, let's look at number 2 here. So we have a 2,000 kilogram truck that's sliding down an icy hill. Okay, so icy hill angled at 20 degrees. Right, so there's our truck. The thing we have to remember about inclined planes is that kind of internal triangle that allows us to calculate the downward component of gravity, okay, or the downhill component of gravity that we call F parallel. Okay, so to do that, we have to remember that gravity, or the force of gravity rather, is the hypotenuse of that triangle. Okay, normal force, which we haven't had a chance to use yet, is this side of the triangle, and we'll end up using it in some inclined plane questions at some point after we talk about Newton's third law on friction. Okay, then this side becomes F parallel. Normal force and force of gravity are offset by the same angle as the ramp. Okay, because normally they would directly oppose each other on a flat surface. Now that I know this triangle, can I calculate the force of gravity? Yeah, it's going to be 19,620 newtons. Okay, 2,000 times 9.81. Everyone okay with that? All right, to find F parallel, it's the opposite side of this triangle, and I know the hypotenuse. Okay, so F parallel is going to be the sine of 20 degrees times 19,620. So 6,710, and I'll keep all the decimals, newtons. Okay, the force of friction is 500 newtons. Which way is that acting? Up the ramp. It always opposes, right? Okay, so now that I've found F parallel, do I need the force of gravity anymore? No, I've already taken it into consideration. It's acting straight down. The object's not moving that way. Okay, I have the 2 forces acting within the plane of the movement of the object. Right, so now I can find the net force by getting the vector sum of all forces. So that'll be 6,710 newtons down the ramp okay, minus 500 newtons up the ramp, or plus negative 500, whichever. Okay, that'll give me 6,210 newtons down the ramp, okay, as my net force. And now I can calculate my acceleration. Okay, acceleration equals F net divided by m. Okay, 6,210 divided by 2,000 kilograms gives us 3.11 meters per second squared downhill. Okay, still the same set of steps. I still did sum of all forces. I still did F equals ma. I had to do a couple of things to get there. Okay, but in the end, I still did those two things. All right, how many of you have done number 3? Okay. In number 3, what are the key words? Constant velocity. What's the net force in question 3? 0. That means the force up the ramp and the force down the ramp are equal. Give you a few more minutes on that. All right, so if we're building the pyramids and we don't have help from aliens with like tractor beams and stuff, okay, then we have to use ropes, ramps, and slaves. That's how the pyramids are built. That's aliens. Okay, so we have an angle here of 10 degrees. We've got these giant stone blocks that weigh up to 5,000, or have a mass, sorry, of up to 5,000 kilograms, okay, and they're being pushed at constant velocities. All right, so the force of friction is 800 newtons. Which way is that acting if the block is going up? Down. Okay, so we have friction acting down. What else is acting down the ramp? Present on every ramp. The parallel force. F parallel. Okay, guys, this force is always there. On an inclined plane, parallel force is always there. Okay, it is the component of gravity pulling down the ramp. Gravity pulls straight down, but boxes move down ramps. Okay, and they do that because part of that force of gravity is directed down or parallel to the ramp. That's where we get this force from. All right, then we've got this applied force upwards. This applied force is going to equal the sum of these two forces because the boxes aren't doing what? They're not accelerating. That means the net force is 0 and the forces up and down are equal. Okay, that's the thing we have to realize here. So really all we have to do is calculate F parallel. Once we have that, we'll know how much force there is down the ramp because we know how much friction there is. All right, so I got 5,000 kilograms, okay, worth of mass there. So we're going to have 49,050. So gravity is 49,050 newtons. So now I can calculate F parallel the same way I always do. The sine of the angle, which is in this case 10 degrees, times the force of gravity, 49,050 newtons. Okay, is 8,517 newtons. Okay. All right, so I've got 8,517 newtons of parallel force. I've got another 800 newtons worth of friction. If I add those two up, that's how much force there is down the ramp. To make it move at a constant speed, I need to pull up the ramp with the same amount. Okay, so 8,512. Okay, plus 800 is going to be 9,312. Sorry, 17, not 12, 17. Okay, newtons. Okay, that's the force down, so it has to be the force up because the net force is 0. Okay, all right with that? Okay, how many people have done number 4? Are we stuck on 4, or do we just need a little more time? A little more time? Okay. What's the key word in 4? Constant velocity. Okay. What force helps you get mass most easily? Gravity. Yeah. If you can find the force of gravity, you can calculate the mass in this question. So this one, similar, very, very similar, in fact, to the last one. Okay. What we have is the car sitting on the ramp. Okay. We know the ramp is angled at 9 degrees. Okay, so we have the car sitting here. We don't know its mass, but here's what we do know. It's being pushed up the ramp at a constant velocity with a force of 800 newtons. So there's 800 newtons up the ramp. How many newtons are down the ramp then? 800. This thing doesn't move at a constant velocity unless the force up and the force down cancel each other out completely and make a net force of 0. Okay, that's what we have to realize. If it says constant velocity, all the forces add up to 0. So we have a frictional force of 100 newtons, which is down the ramp because it says it's moving up. Okay, and that means that F parallel has to be how big? 700 newtons. Okay, everybody follow my logic on that? Okay, so now that I have that, now I can go to my triangle. Remember I said you're going to need the force of gravity if you're going to find the mass? Okay, because we can't use F equals m times a because a is 0. All right, so I've got my triangle here that I always have. Okay, this is 9 degrees, but I know now that this side is 700 newtons. Can I find the force of gravity? Yeah, and once I know the force of gravity, I can calculate the mass of the car. So I'm going to work backwards and find the force of gravity. So force of gravity will be 700 newtons divided by the sine of 9 degrees. Okay, because it's opposite over hypotenuse. Okay, so 700 divided by the sine of 9. Okay, gives me 4,474 newtons. Now I need to divide that by what? 9.81. That'll give me my 456 kilograms.
How do you know when to divide by the sine?
Oh, I manipulated that equation in my head. So I went sine of theta equals opposite over hypotenuse. Okay? Force of gravity was the hypotenuse of the triangle. So I manipulated so the question solved for that. So sine ended up underneath and hypotenuse ended up over there. Does that make sense? All right, questions on that one? I would like you guys to try number 11. That's like the mother of all Newton's second law questions. It involves an inclined plane and a pulley. An inclined plane and a pulley. So we have to remember the rules for an inclined plane, that little triangle. And then we have to remember that because it's a pulley, the net force acts on all of the mass. Okay? Follow that in mind. This one's a little bit tricky, but I think you guys can see if you figure it out. Okay, so if we're looking at this one, I'm just going to kind of set it up just in case some people need a little bit of a push to kind of get going on it here. The forces that are acting, okay, it says here that it's frictionless, okay? If it's frictionless, the only forces acting are F parallel on the 2 kilogram mass and the force of gravity on the 2.5 kilogram mass. Those are the only two forces that are acting. Okay? So, like very simply then, I could simplify this whole thing to look like this. 4.5 kilograms is being pulled this way by the force of gravity on the 2.5 kilogram mass, okay, which is going to be 2.4. Okay, so by the 2.5 kilogram mass, so we've got 24.525 newtons pulling that way, okay? And I've got F parallel pulling this way on that 4.5 kilograms. Is everyone all right with that? Okay, because remember, when we have a pulley, all the forces act on the whole system. Okay, so I got to calculate what F parallel is. So I draw my usual triangle in here. Okay, this side here is going to be 19.62 because it's the force of gravity, 2 times 9.81. Because this angle is 30 degrees, okay, F parallel is going to be the sine of 30, which is 0.5, times 19.62. So that makes F parallel 9.81 newtons. Okay, question wants me to find the acceleration of the 2 kilogram mass. Is it the same or different than the 2.5 kilogram mass? It's the same in magnitude. It's different in direction. The 2.5 kilogram mass is going to accelerate down, and the 2 kilogram mass is going to accelerate up the ramp. Okay, so they will have a different direction, and that's why the question is stated that way. Okay? If it asked what's the acceleration of the system, it would have to say what's the magnitude of the acceleration of the system, because the two parts accelerate in different directions. Okay? Here it's specified a specific mass, so we can give a direction. All right, so if we're going to find the acceleration of the system, we need to know F net, and we need to know what else? Mass. Okay, well we have mass. F net's not going to be hard to find because here's the two forces that add up to F net. 24.525 minus 9.81 should give me 4.905, yeah? No? You're shaking. Sorry, 14, sorry, you're right. Sorry, 14 point what? 715, sorry. 14.715 newtons. Okay, so 14.715 newtons, okay, is my net force divided by the mass of the system, 4.5. Okay, that will give me my 3.26 meters per second squared up the ramp, because we're talking about just that one. Okay, ready? Good with that. All right, I want you to try number 12. Okay, still an inclined plane, still similar processes, except this time you're actually looking for the angle. Looking for the angle of the ramp. A part of what we know about inclined planes is probably going to help you get that. Yeah, you're going to need force of gravity. You're also going to need that parallel. That little triangle that we draw inside the inclined plane every time, that's where you're going to get that angle from. You're going to get how many sides of it? 2. Gravity and F parallel. So you got to figure out how to get them so you can get that angle. Okay, so let's have a look at this one here. So we've got the hill or the ramp that this truck is sliding down. Okay? We know the mass of the truck is 3,000 kilograms. Okay? It says that it's traveling at a constant velocity. What does that mean? F net is 0. Acceleration is 0. F net is 0. The forces up the ramp and the forces down the ramp are the same. Okay? They have to be. That's the only way they could add up to 0. So they tell me that friction is acting up the ramp with 1,600 newtons. Well, F parallel is acting down the ramp. How big is it? 1,600 newtons. There aren't any other forces. It's just those two. Okay, so we just did vector sum of all forces. So now we can move on. Okay, now we need to look at this internal triangle because they're asking us, what's theta? Okay, well, if I'm going to get theta, I have to use this triangle. I'm not going to be able to get Fn. It's supposed to be n. Okay, I'm not going to be able to get that because I don't have the angle. Okay, but I can get Fg because I have the mass. Okay, so I have 3,000. Okay, so that side's 29,430 newtons. This side is 1,600 newtons. Okay, how are those two sides related? What trig function relates those two with that angle? Sine. Right. So the sine of theta equals the F parallel divided by the force of gravity. Okay, I only want theta, so what do I do with sine? Inverse. Okay, so theta will equal then the inverse sine of F parallel divided by Fg, okay, which will be inverse sine of 1,600 divided by 29,430 newtons. That should give me 3.116 degrees. Is that right? Okay. Now, why are there 4? Because my answer is wrong here. Okay. Why are there 4 significant figures here? Right. I used 1,600, 4 significant figures. 3,000, 4 significant figures. Okay. But I used 9.81. Well, it's not in the question, but it's a constant. Where did I get it from? My formula sheet. What do we say about significant digits for anything that comes off the formula sheet? They're infinite. Right, okay? Your formula sheet you consider to be an absolutely accurate source of information whose numbers do not count towards your significant figures. Okay? We did an example like that just the other day where that happened as well. So it happens once in a while. You need to be on the lookout for it. In this case, this answer would be correct to 4 significant figures. All right, questions on that one? All right, on Monday, and I'm going to start it today, but on Monday, we're going to talk about a lot about Newton's third law. Okay, and then we'll talk about friction a little bit, and then we're going to do an assignment on Newton's laws, and we're done with Newton. Okay, over 2 weeks of Newton by that point. Okay, then we're going to move on to work energy theorem and conservation of energy, which are reviewed from Science 10. Okay, and then we actually don't expand on them all that much. Right, so they're very similar to what you would have done in Science 10. Okay, Newton's third law. Newton's third law is the most often misquoted or misapplied statement that I've ever heard. Okay? Because people are always trying to apply it to some sort of sociological application. Okay? Newton's third law says this: every action has an equal but opposite reaction. Okay? That's Newton's third law. But people apply that to these weird situations it doesn't apply to. Okay, like if I say something awful to somebody and they slap me in the face, well, every action is opposite reaction. No, you said something awful, they smoked you, they deserved it. That wasn't equal and opposite. It's appropriate. Okay, but okay, you should never hit somebody, but you shouldn't also say something nasty. So Newton's third law deals with every situation where forces are involved, because forces always act in pairs. Okay? They always act in pairs. So the most common situation would be if I set something on a table. If I set something on a table, let's say is 2 kilograms, gravity will pull down with 19.62 newtons worth of force. But what does the object do? If I set it on the table, it's just going to sit there, which means the net force acting on it is. The only way for that to be true is if there's an oppositely directed and equal magnitude force acting upwards. That's what we call the reactive or normal force. Okay, Fn. Right, is our normal force, and it is there because all forces act in pairs. It's also the reason why in a fight people break their hands. Okay, even if I land a good punch on somebody and knock them out cold, there's a high likelihood that I will break the bones in my hand doing so. Because when I hit them in the face, their face hits me back. Okay? It's the same in hockey. If I hit somebody into the boards, do I still feel that in my shoulder? Yes, because when I push on them, it pushes back on me. Okay? Hopefully what happens to me is I bounce off, okay, and I keep skating and they lie in a heap. Okay? Because hopefully what happened was I hit them hard enough into the boards that the equal and oppositely reactive force of the boards knocked them down. Okay? That's all I can hope for. Okay? Does that sort of make sense? So you never get away scot-free when you exert a force on something or somebody. It always exerts a force back. Because why right now, you can feel your seat. Okay, we'll talk more about that on Monday.